Hi there, Mr. Sutton here, bringing you the AB Calculus 6-3 Extra Practice Number 2 solutions on slope fields. On this free response problem, we're given the differential equation dy over dx equals x parentheses y minus 1 over 4, so that'll be interesting to work with. For our first task, we're being asked to create a slope field for this, given the 12 points in this graph. So although it's not required for this, I always like to make a table, and I always lay it out with the x and y values the same way this grid is laid out that they've given me. So I've got my own little grid, and I've got all the y values from 3 down to 0, just like we have here, and also negative 1, 0, and 1 for the x values. So let's see, I'm just going to go one column at a time. So starting here, I have the x value negative 1, and I'm plugging different y values in. So with an x value of negative 1, we've got, let's see, negative 1 times 3 minus 1 over 4. So that's negative 1 times 2 over 4. So that's negative 1/2. And then now we've got negative 1 times 2 minus 1 over 4. So that's going to be, let's see, negative 1/4. Next we have negative 1 times 1 minus 1 over 4. That's a 0. And then this is going to be negative 1 times negative 1 over 4. That's positive 1/4. All right, so let's move on to the next one. For this one, all the x's are going to be zeros all the way down here. Well, if we're multiplying anything by 0, it's going to end up being 0. So it doesn't actually matter what y is. This is just zeros all the way down this column. So that saves a little time if you can see patterns like this. And then for the next one, now we have a positive x value instead of a negative one. So since for all these y values, we're going to end up with the same thing in this parentheses. The only thing that's going to change is we're multiplying it by a positive 1 outside instead of a negative 1. So this negative 1/2 will now be a positive 1/2, and this will be a positive 1/4. 0 is still 0, and we have now a negative 1/4. All right, let's go through and actually graph all these out in our slope field. So starting in the upper left here, we have a slope of negative 1/2. So just kind of drawing my tangent line in my head here, we need to go down 1 and over 2, so a tangent line kind of like this. And then next we have a negative 1/4. Well, now we're going down 1 and over 4, so it's going to be less steep than the one we just drew, which is kind of hard to draw, but just do the best you can, I guess. This next one, there's really no wiggle room. You need to draw a horizontal line for 0. And down here, positive 1/4 is kind of it's just the mirror image of this negative 1/4 you drew. So now this next row, this next column, we have all zeros. So this is all horizontal tangent lines along the y-axis. And on the other side here, these are all positive versions of the slopes you drew at x equals negative 1. So we have positive 1/2, positive 1/4, 0, and negative 1/4. So there's our slope field. For this part of the problem, we have y equals f of x is the particular solution to this differential equation with an initial condition of 1, 3. We just want an equation for the tangent line to the graph at 1, 3, and then to use it to approximate f of 1.4. So general setup for a tangent line, a linear approximation, we're going to have L of x equals, we're going to have our point of tangency, so f of 1 plus f prime of 1 times x minus 1. Basically f of a plus f prime of a times x minus a sort of setup, where 1 is the x value that you actually know something about. Now plugging in a few values for this. We actually already know f of 1. They gave it to us. It's 3. We'll plug that in a sec. But f prime of 1 we'll have to do a little more work to find. So for that, we're going to have to use our differential equation up here. Now this is a little tricky because this differential equation takes both x and y values. So when I do f prime of 1, I'm not just plugging in the x value 1, I'm also plugging in the y value that goes with it, the y value 3. So f prime of 1 up here is going to look like the x value 1 times y value of 3 minus 1 all over 4. So we're plugging in a whole point here. And then this is going to be, let's see here, 1 times 2 over 4. So that's just 1/2 if you reduce it. So plugging things back in, we have L of x equals 3 plus 1/2 times x minus 1. This is the equation of our tangent line, and that was part of the question, was to come up with this. Now we need to use this to approximate f of 1.4. So I'm going to write f of 1.4 is approximately equal to 3 plus 1/2 times 1.4 minus 1. You will not get full credit if you write equals here. This is approximately. It's an approximation. Truth in advertising. So now you can actually leave it like this because you have all constants. Or if you wanted to, you could simplify. This is really, let's see, 0.4. Half of that is 0.2. 3 plus that is 3.2. For this last part of the problem, they want us to find the particular solution to this differential equation, given that initial condition of f of 1 equals 3. So one thing I notice here in trying to solve this is that I have an output variable, y, in the differential equation. That means I'm going to have to separate my variables, basically get the y with the dy and the x with the dx before I can take the antiderivatives. So to do that, let me divide both sides by y minus 1. So I have dy over y minus 1, or y minus 1 to the negative 1, however you want to write it. And then we'll multiply dx by both sides. So we have 1/4 x dx, if we want to write that stuff on the right side. Now I'm going to take the antiderivative of each side. So on the left side, this is going to be ln absolute value of y minus 1. On the right side, using the reverse power rule, this bumps up to an exponent of 2. Dividing by that, we now have 1/8 x squared plus c. Don't forget the plus c. At this point, we're going to have to find the c value by plugging in this initial condition of 1, 3. So on the left, I have ln of 3 minus 1. And on the right, this is now 1/8 times the x value 1 squared plus c. So we have ln of 2 minus 1/8 if we get c by itself. And I can't really simplify that too much more. So let's go back, and we're actually about to plug this whole thing in for c. Before we do that, though, let's take care of this absolute value because we can't have that in a particular solution. So taking a look at our initial condition, we see that y has a value of 3 for that initial condition. If that's the case, then the stuff inside this absolute value, namely y minus 1, is going to be positive, which means that I don't actually need the absolute value and I don't need to negate the stuff inside there to simulate absolute value. I can just rewrite this with a parentheses. So let me just rewrite this then as ln of parentheses y minus 1. And then that's going to equal 1/8 x squared plus my c value of ln of 2 minus 1/8. Almost done. We still need to get y by itself, though. So let me raise e to both sides. So that'll give me y minus 1 on the left, and on the right, I've basically got e to all that stuff on the right. Now, before I solve for y, there's just one more thing I'm going to do to clean this up, and I'm not actually required to do this, but this is just to show you how answers are typically written. So whenever you have an ln of something inside an exponent with an e, you can actually split this off into, let's see, e to the 1/8 x squared minus 1/8 times e to the ln of 2. Now, e to the ln of 2 is just 2, so we can bring a 2 out in front here. And then what's left inside, since we have a common denominator, you could just write this as 2e to the x squared minus 1 over 8, if you want to really fully simplify that as much as possible. And then just add 1 to the other side and call it a day. On this problem, they just want us to sketch the slope for this differential equation. So we have a slope field here, and it looks like there are, 25 different points that we need to put this in. So I'm going to set up my own little table grid organized the way this graph is. So I've got all my x values going from -2 to 2, and all the y values going from 2 down to -2. So now let me start in the upper left corner here. So this is an x value of -2 getting multiplied by all these y values. So we have -2. So that ends up really being +2 multiplied by whatever's here. So we have 2 times 2, which is 4. 2 times 1 is 2. 2 times 0 is 0. 2 times -1 is -2. 2 times -2 is -4. Next, we have -1. So that's really just +1 getting multiplied by all these y values. So that's just going to be 2, 1, 0. It's basically the y value, -1 and -2. So that was pretty easy. The next one is even easier because now we're doing 0 times all these y values. So that's just going to be 0 all the way down. And then we have now -1 times all these y values. Basically, that's just the reverse, the opposite version of everything in this -1 row. So now instead of +2, we have -2, -1, 0, +1, and +2. And same deal over here. It's just the opposite sign of everything in this -2 row. So now we have -4, -2, 0, 2, and +4. Now we're going to graph out the tangent lines. So we've got, let's see here, 4, tangent line of 4. So that's over 1 and up 4. Just draw that as best you can. And then slope of 2 is going to be still steep, but less steep. So like over 1, up 2, like this. Next we have 0. There's no wiggle room on that. We need a horizontal tangent line. And now we have -2, and even more steep, -4. Moving over, now we have 2 and 1. That's pretty easy to draw. Just imagine connecting these diagonally. Then we have 0, -1, -2. And finally, well, not finally, we've got this whole y-axis here that has all horizontal tangent lines. Next, we have negative versions of everything in this second column here. So -2, -1, 0, 1, and 2. And then finally over here we've got, let's see, -4, -2, 0, 2, and 4. For this problem, we're trying to build a slope field for this differential equation using the 25 dots in this graph. So let me set up a grid giving me basically my slope numbers for everything here. I'm going to set it up just the way this is set up, with all the x values from negative to +2 and all the y values from positive to -2. So now for this dot up here, this is this upper left corner, we have x value of -2, and we're going to be subtracting all these y values from that, just the way this differential equation is set up. So this is going to be -2 minus 2, which is -4. -2 minus 1 is going to be -3. -2 minus 0 is -2. And you can see there's a pattern here. It just goes up by 1 each time. So this is going to be -1 and 0. Next, we've got -1 minus all these y values. So -1 minus 2 gives us -3. -1 minus 1 is -2. And just like this row, it keeps just going up by 1. So -1, 0, and +1 now. And now we have 0 minus all of these. So you might have noticed that these rows also keep increasing by 1, because the number that we're subtracting stuff from keeps increasing by 1. So this is going to be a -2 here. And then these all go up by 1s. So -1, 0, 1, and 2. This next one is going to be going up by 1, so -1. And then we have 0, 1, 2, and 3. And finally, this goes up by 1 again, going horizontally. So this is now 0, followed by 1, 2, 3, and 4. So graphing all these out, we have our tangent line of -4. So that's going to be down 4 and over 1, something that steep. -3 is, let's see, down 3 over 1, so a little less steep. Still pretty steep, though, kind of hard to tell the difference. And then we have -2, -1, and finally 0. And then going over here, we've got -3, -2, -1, 0, and +1. And we just keep going, so -2. This is going to be -1, 0, 1, and 2. And then over here, this is -1, 0, 1, 2, and 3. And finally, we have 0, 1, 2, 3, and steepest of all, we've got 4. On this problem, I'm trying to see which of these differential equations could represent this slope graph they've given us here. So I'm going to look up a few slope values in this graph and then see which of these answer choices I can eliminate based off of that. So for example, let me look up 0, 0 in this graph. In the graph itself, I see that we have a horizontal tangent line on the origin. So that's a slope of 0. Let's now plug 0, 0 into all these differential equations and see what actually gives us 0 back. So for choice A, we get 0 back. For choice B, 0 times 0 is 0. Choice C, we have 0. Choice D, we have 0 over 0, which comes out undefined. So we can eliminate choice D. And then choice E, -0 times 0, still works. So let's try something out this time that has a different x and a y value, like 1, 2. So in the graph, that appears to have a slope right here of about 1. At the very least, it's positive, but I think we can conclusively tell here it's 1. So checking that out in my answer choices, for choice A, that would be 1 plus 2, which is 3. There's no way that that's a 3 for a slope. That's too steep. Choice A is too steep. B, we have 1 times 2, which is 2, still too steep. For choice C, this would be 2 minus 1, which comes out to 1. So choice C is still good. D, we already eliminated. Choice E, this would be just a negative slope, so that's not going to work. So we can eliminate then A, B, and E, leaving us with just choice C. For this problem, I'm trying to match one of these differential equations with this slope field. So let me take a look at a few points on here, see what the slopes are, and see what I can eliminate from my answer choices. The easiest one that I always like to use is the origin, 0, 0. In this case, if we look up the slope of 0, 0 on the slope field, there's nothing given there, really nothing given anywhere on the y-axis at all. So that means our slope does not exist at 0, 0. So taking a look at my answer choices, let me see which ones also do not exist when I plug in 0 and 0. So A still comes out to something that exists, 0, 0. Well, 0, 0 gives us 0 for choice A. So we can't eliminate, we have to eliminate A, actually, because that does exist. B comes out undefined, so that's still in the running. C is undefined, still in the running. D and E actually both give us numbers back, both zeros. So D and E can be eliminated because we needed to get undefined when we plugged in 0, 0. So then A, D, and E are gone. So that's pretty good for testing out our first point. Next, I'm going to test out something like 1, 2, something with a different x and a y value, just to see if I can choose now between, let's see, we're down to B and C. And I noticed that B and C are essentially the same thing, it's just the numerator and denominator are flipped. So by picking different x and y values, I ought to be able to pick one or the other. So now on the graph here at 1, 2, we have a negative slope, and specifically we have a negative slope that seems to be more negative than, say, negative 1. This looks like negative 1 right here at 1, 1. At 1, 2, we are steeper in the negative direction, so less than negative 1. Taking a look now at the different choices that we still have. For choice B, this would give us back a slope of negative 1 over 2, which is not steep enough. So that would be eliminated. Choice C, we would have negative 2 over 1, which that could plausibly be a slope of negative 2 right there. So it looks like choice C then is the best choice. On this problem, we are given this slope field, and they just want us to draw the solution curve, where we have an initial condition of 2, 2. So let me find 2, 2 on here. It's right here at this spot, right about here. So they just want us to draw the curve that goes through there. So basic idea, you just have to follow the tangent lines, and it looks like we're going around in a circle, and you just have to make sure that 2, 2 is included when you're doing this. So here's what I ended up drawing, something like this. So we've got 2, 2, and just sort of following the tangent lines as best we can. It doesn't look like there's any exact tangent lines for us to follow there, but we're following pretty much where we think the in-between tangent lines would be, since they didn't give us a point that was actually on any of the tangent lines to begin with. So we're just doing the best we can with what they've given us.